A very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course classroom discussion topic. So the today's topic is to discuss about the importance of the steady flow energy equation, and the motivation towards this topic is it is very important to be note that how all engineering devices will work and perform according to the steady flow energy equation. So the outcome of this lecture is, so every student should be in a position to derive the steady flow energy equation and explain what are the assumptions which are involved while deriving the steady flow energy equation. So this steady flow energy equation is basically coming to the picture whenever we are applying the first law of thermodynamics to open systems. So far we studied the applications of first law of thermodynamics to the closed systems. So now in the today's class, we are going to discuss about for the open systems. So open systems, that is, I already told you that almost all engineering devices are examples for the steady flow energy equation. So that's why what are the assumptions which are involved while deriving the steady flow energy equations? These are very important ones. So the first one is the mass flow rate throughout the system will remain constant. So that is the mass flow rate of the working fluid throughout the system will remain constant. That is the first important assumption. The second important assumption is the fluid is uniform in the composition. That is, its chemical composition will not vary whenever it is flowing from inlet to the outlet. So we are assuming, so it is a uniform in the chemical composition throughout the working, that is throughout the system whenever it is flowing from inlet to the outlet. Next one, the only interaction between the system and surroundings are only in the form of work and heat transfer. Next one, the state of the fluid at any point will remain constant with respect to the time. That is, you take whether it is the pressure, volume, temperature, or any other thermodynamic property values at a particular point of the time. So these are basically taken as constant with respect to the time. That is important. That is the steady flow. Steady flow means the thermodynamic parameter values will not vary with respect to the time. That is very important one. That is, at a given point of the time, the thermodynamic parameter values will remain same. That is the meaning of the steady state, because whenever you are conducting some experiments in the heat transfer laboratory, always we have to wait till the equipment attains the steady state. That is, let us say that now the time is 10:30 a.m. At 10:30 a.m. now you have noted down, that is, what are the thermocouple value. That is, let us say that some 12 thermocouples are attached to a particular equipment. So at 10:30 a.m. you have noted down T1 value, T2 value up to T12 values. Then after some 15 minutes of the time, once again you are checking the values. So there is some variation in the values. Once again you are noting down the values at 11 o'clock. So let us say that T1 to T12. So you have noted down the values at 11 o'clock. Then 11:15 also you have noted down. So there is no variation. That is the T1 value, whatever the value is there at 11 o'clock, the same value is there at the 11:15. Similarly, T2 to T12 also, the same values are there at 11 o'clock and at 11:15 and at 11:30 and 12 o'clock. That is, the values are remains constant with respect to the time. So that's why now you can say that the equipment attains or reached the steady state condition. Now, after obtaining the steady state condition only, you have to note down the final readings for our calculation purpose. So that is the procedure normally what we are doing in our heat transfer laboratory. So since the steady state term is basically came here, that's why I'm explaining what is the importance of the steady state. That is the time. With respect to the time, the parameters will remain constant. It will not vary with respect to the time. So in the analysis, only potential and kinetic and flow energies are considered, not other energies. So here, just to consider a diagram here. So here it is the inlet datum level. Inlet datum level is represented by Z1 and the exit datum level is represented by Z2. So it is the changes in the potential energy, normally mgZ1 and mgZ2. So these are the values. So here it is the inlet and here it is the outlet. So it is a thermodynamic system where the working fluid is basically flowing within this particular the thermodynamic system, and it is separated by a boundary. So whenever you have taken this particular figure, so then how can we write down the steady flow energy equation per unit mass of the substance? So here you can write down that, so H1 is nothing but is a U1 plus P1 V1. So U1 plus P1 V1, we have taken it as the H1. H1 plus C1 square by 2, but in some of the textbooks they have taken it as the V1 also. So because the velocity of the fluid here we have taken as the C1 and C2 at inlet and exit, but some of the textbooks they have taken the V1 and V2 also, so don't confuse between the V1 and V2. So H1 plus C1 square by 2 plus ZZ1, it is potential energy and it is the kinetic energy, and here it is the summation of the internal and flow energy, that is nothing but the enthalpy. That is, whenever you are considering the steady flow energy equation, that is, it is the summation of all energies at inlet condition, it is equivalent to the summation of all energies at outlet condition. So just you see here enthalpy at inlet and enthalpy at outlet. Kinetic energy at inlet, kinetic energy at outlet. Potential energy at inlet, potential energy at outlet. But here we are giving some amount of the heat input and here we are having some work output. So that is heat transfer to the system. So that is heat transfer to the system and the work done by the system. So work done by the system is always positive. Heat transfer to the system is always positive. So that's why the heat is added to the system. So heat is added to the system. That's why we have taken plus delta Q, and work is developed by the system. That's why it is a plus delta W. So broadly we can say that H1 plus C1 square by 2 plus ZZ1 plus delta Q is equivalent to H2 plus C2 square by 2 plus ZZ2 plus delta W. So most of the times he can say that the datum levels are same. So but here there is a difference between the Z1 and Z2, but in some of the cases they will take some, that is the same heights for Z1 and Z2. So when the Z1 and Z2 heights are same, then automatically the change in the potential energy can be neglected when Z1 and Z2 are same. So then ZZ1 and ZZ2 parameters may be neglected. So whenever you are neglecting these parameters, we are able to have H1 plus C1 square by 2 plus delta Q is equivalent to H2 plus C2 square by 2 plus delta W. So that is the steady flow energy equation. And what are the parameters? Just now I told you that C stands for the velocity of the fluid, Z is equivalent to height above the datum level, P is pressure of the fluid, U is the internal energy per mass of the substance, PV is equivalent to the flow energy. And here the continuity equation is very important one. The continuity equation says that mass flow rate is equivalent to A1C1 by small v1 is equivalent to A2C2 by small v2. It is known as the continuity equation. It is very important one to find out the mass flow rate of the substance or the diameter, because A1 is equivalent to the cross sectional area, that is equivalent to pi by 4 d square. So if you want to find out the exit diameter or the inlet diameter also, you can find out from this particular the equation. So the mass flow rate of the substance can be found out by using the continuity equation. So m dot is equivalent to A1 C1 by small v1 is equivalent to A2 C2 by small v2, where small v1 and small v2 stands for the specific value. So it is the steady flow energy equation. Now in the next class we are going to discuss about the applications of the steady flow energy equation, because these are very important one, because I told you that all engineering devices will come under the open systems and all these open systems will work according to the steady flow energy equation. So how they will work and how can we find out the performance of all those engineering devices according to the steady flow energy equation, so that we will discuss in the next class. I hope you understood the concept of the steady flow energy equation very comfortably. So I will meet you in the next class. So thank you very much for listening this